Hello, today we'll be discussing regarding the problems related to vapor compression systems on how to solve the problems either using the analytical method or using the graphical method. So first of all, we'll be discussing regarding the ideal vapor compression system problems or simply saturated VCRS. So you can see here the important components of a simply saturated or ideal VCRS being a compressor, a condenser, an evaporator, and an expansion valve. So first of all, before entering the compressor, the refrigerant coming out of the evaporator will be simply saturated vapor or will be represented on the curve as shown here, and it will be at a temperature equivalent to the evaporator temperature or at a pressure equivalent to the pressure of the evaporator. Then as the vapor passes through the compressor, it will be compressed isentropically, that is entropy is equal to constant. As such, the saturated vapor now gets converted to superheated vapor to state 2 as shown here. Then when moving to the condenser, the refrigerant will be cooled either by air or water. Basically, as such, the refrigerant will loses its heat gradually. First of all, the superheated vapor gets converted from 2 to 2 dash, or gets converted to saturated vapor as shown here. Then again, the cooling air or cooling water will be circulated in the condenser, where the refrigerant will start to change its phase, and finally it will be coming out of the condenser as a saturated liquid or state 3 as shown here. Then it will be passing through an expansion valve where it will be undergoing a isenthalpic expansion or an expansion at constant enthalpy, that is from 3 to 4. That is the enthalpy of the refrigerant before coming into the expansion valve and going out after the expansion valve remains constant as shown here. Also, here we can also see that the condensation, pressure and temperature etc. takes place at a pressure of Tc, Pc respectively, which will be either specified in the problem. Then this the vapor, the refrigerant, which will be actually a mixture of liquid and vapor at state 4, will be sent to the evaporator. From there it will be absorbing the heat from the space to be refrigerated, refrigerated. As such, it will take the heat and liquid gets converted to vapor, and it will be going out of the evaporator as saturated vapor as shown in the pH diagram. Also, the COP of the system is actually given by refrigerating effect by work done, where refrigerating effect is mainly concerned with the evaporator of the evaporator or the evaporation being done, and work done is the work given to the compressor, and that can be written in terms of enthalpy difference as refrigerating effect, which is equal to H1 minus H4 by work done, which is equal to H2 minus H1, which will give the COP of a ideal VCRS cycle or a simply saturated VCRS cycle. Then coming to the important relations, apart from COP, there are also other specifications or other properties which we need to find out while doing the problems, and which is actually given by, first of all, 1 ton of refrigeration. That is, the refrigerating effect will either be given in tons of refrigerant, which we need to convert into standard units by multiplying with either 12,600 for converting to kilojoules per hour, or multiplying with 210 for converting that into kilojoules per minute, or multiplying with 3.5 for converting that into kilowatts. Then mass flow of the refrigerant we'll assume to be m dot, and we'll take the value as kilogram per second for easing our calculation, or it can also be done written in terms of kilogram per minute. That mainly depends upon the values which take as 210 or 3.5 for converting this ton of refrigeration. But usually it is easier to convert the mass flow of refrigerant in kilogram per second for easily finding the results in a one step. Then the refrigerating effect, or the tons of refrigeration, we can see the evaporator is responsible for the refrigerating effect. This will actually be given by the mass flow of the refrigerant in kilogram per second into the enthalpy difference, that is H1 minus H4, that is the enthalpies or the enthalpy of the states associated with evaporation, and this enthalpy will be specified in kilojoules per kilogram, and the refrigerating effect can be got in terms of kilowatt. So converting 1 ton into 3.5 kilowatt would be a better idea. Then the compressor power, or power given to the compressor, as we can see, this is a isentropic compression. Also, for power given to the compressor will be given by mass flow in kilogram per second into enthalpy difference, that is H2 minus H1, that is the states which are associated with the compressor or compression. Then heat rejected by the condenser, we can see condensation actually occurs from state 2 to 3 as shown in the pH diagram at constant pressure and temperature. So heat rejected by the condenser will be given by mass flow rate of the refrigerant in kilogram per second into H2 minus H4 or H3. Here we can see H3 and H4 being the same value, since 3 to 4 is constant enthalpy expansion. So H2 minus H4 or m dot into H2 minus H3 both bears the same result, and all these things will be got in terms of kilowatt respectively. Mind you, the mass flow rate should be taken in kilogram per second and enthalpy should be taken in kilojoules per kilogram for attaining the values in kilowatt. Then some of the other important relations mainly includes our finding the enthalpy at state 2. Here we can see in the process the evaporation takes place between 4 to 1, and this evaporator will be kept at a temperature something like PE and pressure PE as indicated in the figure, that is the lower pressure or temperature in the system, and the condensation or condenser will be kept at a temperature correspond to TC or PC as shown here, that is higher pressure or higher temperature in the system. But here what we can see is that 4 and 1, the temperature of the evaporator and pressure of the evaporator can be taken, but for point 2 we already see simply our saturated vapor is being compressed to a supersaturated vapor. So here the temperature difference between 2 and 2 dash will be different, that is T2 and T2 dash will be having some slight difference, and that will be the degree of superheating as we require. So even though the point 3 and 2 dash, that is the point lying on the end of the line, or that is the point lying as supersaturated liquid, we can see that 3 and 2 dash will be equal to the temperature same as the condenser temperature, but here the temperature of point 2 will not be equivalent to condenser. Rather, the temperature of the vapor at state 2 will be slightly greater than the condenser temperature by 5 to 10 degrees Celsius. So by finding that temperature only, we could find what is the enthalpy of H2, which is actually required for finding the work done and hence finding the COP. So for that, we'll be using two relations based upon this enthalpy difference and entropy difference, that is enthalpy between the point 2 and 2 dash. 2 dash is nothing but the point joined between the condensation from superheated vapor to saturated liquid, where in between it will be cutting our saturated vapor line or the curve. From that we'll be marking this 2 dash, and this enthalpy difference is actually given by the specific heat of the refrigerant vapor into the temperature at 2 minus temperature at 2 dash. Similarly, entropy is given by S2 minus S2 dash is equal to specific heat of vapor into ln T2 by T2 dash. Since this is at constant temperature, that is why we are getting this simplified formula. So hence using these two equations, we can initially find T2. From that, we can find H2 for calculating our entropy difference. Also, we know from process 1 to 2, this S1 is equal to S2. Also, from S1 can be easily found out from the chart or the graph. Similarly, the entropy at S2 dash can also be easily found out from the chart or curve. Also, this S2. So, using this entropy relation, we can find the temperature at 2 in Kelvin, and substituting this back to our enthalpy equation, where H2 dash and T2 dash is known, where T2 dash is nothing but our condenser temperature. We can easily find the value of H2 or the enthalpy of 2 subject to the condition that the specific heat of vapor refrigerant, that is CPV, should be given in the question. Then another question will be regarding how to find the bore and stroke of the cylinder. Usually for the compressor cylinder, bore to stroke, that is D by L ratio, will be given for simplifying our formula. And for that, we need to find the piston displacement volume in cubic meter per second. That is actually given by the mass flow rate of the refrigerant in kilogram per second into its the specific volume of the refrigerant at state 1. That is, state 1 actually specifies the specific volume of the refrigerant that is entering the compressor in meter cube per kilogram divided by the volumetric efficiency. Mind you, if the volumetric efficiency is not given in the question, we have to assume that equal to 1. Then there is also another formula for finding the piston displacement in meter cube per second as LANK by 60, where L is the stroke length of the cylinder and area is the cylindrical bore, which is equal to area of the cylindrical bore, which is equal to pi by 4 d square in meter square. Then K is the number of cylinders. If nothing is given, we can assume that to be 1. Then small n, which is equal to just simply the speed of the compressor crank in RPM in case of single acting compressor. If the compressor is double acting, we need to multiply the speed with 2 in case of our double acting compressor, and we'll be equating these two equations, that is equation 1 and equation 2 will be equated, and this D by L ratio will be substituted for getting our diameter and stroke of the cylinder. Then we'll be coming to a question based upon an ideal vapor compression system. Here, an ideal vapor compression system uses R12 as refrigerant. The system uses an evaporator temperature of 0 degrees Celsius. This is the important point to be noted, and a condenser temperature of 40 degrees Celsius. The capacity of the system is 7 tons of refrigeration. Determine the mass flow of the refrigerant. Second part, power required to run the compressor. Third part, heat rejected in the compressor. Fourth part, COP of the system and Carnot COP. Here they have given take the COP for superheated vapor, that is between the state 2 and 2 dash as 0.6 kilojoules per kilogram. Since the specific heat of the superheated vapor is given in the question, it is expected to answer the problem by analytical method. So here, first of all, our refrigerating effect is actually given by 7 tons of refrigerator. Then our evaporation temperature is actually given by TE as 0 degrees Celsius or 273 Kelvin. Also, the condenser temperature is given by 40 degrees Celsius, or which will be equivalent to 313 Kelvin. So we need to take the properties of the refrigerant, that is R12, at corresponding to 0 degrees Celsius and 40 degrees Celsius from our standard data book. And for my purpose, I am actually taking the data from Dom Kundwar and Dom Kundwar. So taking those values, this actually comes something like this. This actually comes something like this, where the important values mainly to be taken mainly includes at 0 and 40 degrees Celsius, that is the evaporator temperature and condenser temperature. First of all, the VG, that is the volume of the vapor at saturated vapor line, which will be equivalent to 0.0555 meter cube per kilogram. Then the specific enthalpy corresponding to 0 degrees Celsius, that is HF, HFG and HG. HF, that is volume of the fluid corresponding to the evaporator temperature in saturated liquid line. Then Hg, the volume of the vapor corresponding to the specific enthalpy of the vapor corresponding to the saturated vapor line, and the value HFG between this Hg and HF in case our points or states goes inside the curve or located inside our phase change curve. Also the specific entropy, that is SF, that is entropy corresponding to the saturated liquid, and SG, and entropy corresponding to the saturated vapor, and difference between that. SFG or latent specific entropy. HFG can also be written as latent heat. Also, these values are actually taken from the table, or tabling this value would be better for doing the problems corresponding to 0 degree Celsius and 40 degree Celsius. Then in our given question, we have the refrigerating effect as 7 tons of refrigerator, that which will be converted first of all into kilowatts by multiplying with 3.5, which actually gives 24.5 kilowatts. That is, the heat absorbed from the evaporator by the refrigerant is equivalent to 24.5 kilowatt. Then next, for finding the COP and all, we must find the enthalpies at point 1, 2, 3 and 4. So first of all, for this ideal vapor compression cycle, we'll be finding the enthalpies at point 1, enthalpies at point 1, 3 and 4 respectively, that can be easily find out either using the chart or using the tables. So similarly, H1, here for H1, we know the evaporator temperature is 0 degrees Celsius. Also for condensation, we know the condenser temperature is 40 degrees Celsius. So H1 is nothing but the line on the curve is nothing but the enthalpy or Hg value corresponding to 0 degrees Celsius for our refrigerant R12, which is nothing but 187.53 kilojoules per kilogram. Similarly, H3 value, which is nothing but our we know that the 3 is actually lying on a point corresponding to temperature 40 degrees Celsius, that is condensation temperature. Also 3 is lying on the saturated liquid line, that is on the right side, on the left side of the critical point. So H3 is nothing but HF value corresponding to 40 degrees Celsius, so which is nothing but 74.59 kilojoules per kilogram. And similarly, H4, we know that 3 to 4 is isenthalpic expansion process. So 3 and 4 will be having same enthalpies. So H3 will be equal to H4, which will be equal to 74.59. So easily we could find the 3 enthalpies 1, 4 and 3 respectively. Now we need to find the enthalpies corresponding to the point 2. For that, we will be, first of all, we know the temperature at 2 dash, or that we already just told you that the temperature at 2 dash will be nothing but the temperature of the condenser. Up to 2 dash, it will be temperature of the condenser. Then going away from 2 dash towards the right, the temperature slightly changes, or a slight degree of superheating will be there. So temperature at 2 dash is nothing but 40 degrees Celsius, which we are converting this into Kelvin, that is 313 Kelvin respectively. Then we need to find the temperature at 2. For that, we need to use the enthalpy or entropy relations, which was stated in the above slides. Also, we can easily find the enthalpy at 2 dash, which is nothing but, since it is lying on the vapor line, enthalpy at 2 dash is nothing but Hg at the condensation temperature 40 degrees Celsius or 313 Kelvin, which is actually given by 203.2 kilojoules per kilogram. Then also we know that for point 1 and 2, that is isentropic compression, the entropy remains constant. So for point 1 and point 2, the entropy of both the states are actually equal actually. So entropy of the point 1 can be easily find out from the table as S1 is equal to nothing but the enthalpy of the supersaturated. So enthalpy of the saturated vapor corresponding to 0 degrees Celsius, which is nothing but 0.6965. Similarly, we also need to find the entropy at point 2, which is nothing but Sg at 40 degrees Celsius. That is, it is also lying on the saturated vapor line. So S2 dash is nothing but 0.6825. Now, actually, similarly, this S2 and S1 will be same as 0.6925, and the entropy at S2 dash will be nothing but 0.6825. Also, we know the temperature T2 dash, so we can use our entropy temperature relation as S2 minus S2 dash is equal to Cp into log T2 by T2 dash. The Cp is actually given in the problem as 0.6 kilojoules per kilogram. So substituting this value, S2 minus S2 dash, that is 0.6965 minus 0.6825 is equal to CPV 0.6 into log of T2, that we need to find out by T2 dash, this is 313, and taking the anti-log etc., we can get the temperature at 2 as 320 Kelvin. That is, compared to the condenser, it is slightly high on the higher side by 7 degree Kelvin or 7 degree Celsius. That is, there will be a slightly superheating. So since we know the temperature at T2, the enthalpy at 2 can be calculated by knowing the enthalpy at 2 dash. Already the enthalpy at 2 dash is nothing but Hg corresponding to 40 degrees Celsius, which is nothing but 203, plus this CPV value is nothing but again 0.6 into T2 minus T2 dash is nothing but 324.4 minus 313, and just subtracting, multiplying and adding the above, we'll get the enthalpy at 2 as 207.64 kilojoules per kilogram. So we have just find out the enthalpies and we have tabled the values as H1 is equal to 187.53, H2 is equal to 207.64, H3 is equal to 74.59, also H4 is equal to 74.59 in kilojoules per kg. Then coming to our next part, we need to first of all find the mass flow rate of the refrigerant. Mind you, the mass flow rate of the refrigerant is always linked with the refrigerating effect. We know from the previous figure that the refrigerating effect is nothing but concerned with the evaporation or the change of state from state 4 to 1. So for finding the mass flow rate of the refrigerating effect can be written as mass flow rate of the refrigerant in kilogram per second into H1 minus H4. And refrigerating effect, we already know that is 24.5 kilowatt, which is equal to mass flow into H2. H1 minus H4, 187 minus 74.59. Upon simplification, we'll get the mass flow rate as 0.217 kilogram per second. But usually we need to write the answer in terms of kilogram per minute. So multiplying with 60, it gives 13.02 kilogram per minute. But for finding all other values, mass flow rate in terms of kilogram per second is easier for our calculation. So we'll be using mass flow rate as 0.217 kilogram per second only. Then to find the compressor output, we know the compressor is actually concerned with the state 1 to 2 isentropic compression. So power in kilowatts can be given as mass flow rate of the refrigerant in kilogram per second into H2 minus H1, or substituting the values 0.217 into 207.64 minus 187 gives the value to be 4.36. Similarly, to find the heat rejected by the condenser is actually concerned with the state change 2 to 3. So the heat rejected by the condenser in kilowatts is given by again mass flow rate into H2 minus H3, which gives 0.217 into 207.64 minus 74.59, which gives the value to be 28.87 kilowatt. Then we'll be coming regarding the part to find the COP of the VCRS system. We know that the COP is equal to refrigerating effect by work done. Already the refrigerating effect is actually given by 24.5, and work done, refrigerating effect is given by 24.5, and work done or power required is given by 4.36. So either we can use that formula or we can use that formula. That is, here we got the refrigerating effect at tons of refrigeration as 24.5, and work done or power at 24.5 kilowatts, or work done or power in terms of kilowatts as 4.36. Either we can directly substitute like this, or we can use our general formula, that is refrigerating effect enthalpy difference H1 minus H4 divided by work done, enthalpy difference H2 minus H1. Both will be getting the same answer as something like 5.62. Then the last part, to find the Carnot COP, we know that our refrigerator is actually working between 0 degrees Celsius and 40 degrees Celsius, that is evaporator temperature and condenser temperature. Using that concept, this Carnot COP, the Carnot COP is actually given by the evaporator temperature, that is lowest temperature T2, by the difference between condenser and evaporator temperature T1 minus T2, higher minus lower. So that And mind you, the temperature should be in Kelvin respectively. So this gives 0, 273 divided by 313 minus 273, or the Carnot COP will be higher compared to the actual COP as 6.82. So that is a simple problem based upon ideal or saturated VCRS. Thank you.